Good afternoon. We're gonna start to calculate a one-way slab to know the reinforcement. So we have this slab and it's simply supported on the major side, along the major side. It will be 50 meters the major side, 6 meters the minor side. Here on cut you can see this is the slab and this supported here by reinforced concrete bricks or some beam. So to calculate the total depth we can use this equation L by 20. Give us, this will help control the cracking, so and the formation, so will help in many problems. And the effective depth, it's the total depth subtracted the clean cover and subtracted half of the diameter. This we can say for this dimensional slab it's approximately h minus 0.03 meters. It's 3 centimeters. Let's consider that. And what will give us 27 centimeters for effective depth. We're gonna use a concrete of C2530, so the FCK will be 25. The FCD it's divided by a safety factor of 1.5. We're gonna use for the reinforcement steel A400 or S400, avec we want to call it. That is the F450, 435, could say F400. So the characteristic value here of the strength of the tensile for this iron will be 400. The safety factor for FYD, to get the FYD we have to use a safety factor of 1.15 to give us 347 megapascal. So okay, we can consider since this slab is supported on two opposite sides, is immediately, you can say automatically, a one-way slab. It's here, it doesn't have support on this side. So we're gonna consider loads for this calculation. The self-weight, that is the total depth multiplied by 25, the density of the concrete. For fourth finish, like tiles or something, we can consider 1.5 kilonewtons per square meter. We will not consider live load, so 0. This could be an office, so if it was office we could consider like 3 kilonewtons per square meters. And how it goes, the function where the slab is being used and which type of building, it can increase to 4, 5 kilonewtons. Here we're gonna, just for the calculation, use like it's 1.9. So a way to know if it's a one-way slab, it's usually dividing the longer span by the minor span, and if it's bigger or equal to 2, it's a one-way slab. In this case we divided 15 by the 6, would give us 2.5. So it's a one-way slab. That's something that we already know this will mean. And in this case, so the main reinforcement beyond the cut will be here on the bottom. Due to this kind of support. If you the main reinforcement will be along the shorter span in this case. So if you have this structure, it's simply supported by the beams on the sides. The moment this load that we're gonna calculate in ultimate limit state will generate a positive bending moment here, like this. And what it will mean, this moment will be factor, because it will be on the ultimate limit state. It's that it will be the forces weight factor multiplied by L elevated by 2 divided by 8. And since it's positive, this is why we have to put here reinforcement on the bottom of the section of the slab. This is why it gets here reinforcement. We'll have here to put a reinforcement tool on the sides due to avoid cracking, because when there is deformation here, since there will be rigidity here on the supports, it will have the tendency to crack when happen here some deformation, and it can't rotate here because of the rigidity. This is why here on the top we have to consider to put some reinforcement tool. It's not necessary in the calculation, I repeat, but to execute the calculation it's only needed this main reinforcement, but for one-way slab, but we need to put this reinforcement here on the support to avoid this cracking near the support. Okay, so we are considering this 1.9, but it should be 3. Let's go. According to each code of anyone, they will know what they should use if it's for office, residence, shops or something. So we have to check for the ultimate limit state to get the reinforcement for this slab. And we start by factoring the loads. That is the permanent loads multiplied by 1.35 plus 1.5 multiplied by the variable loads and 1.5 by the live load in the Eurocode. And here we took these values and we multiply, give us 15 kilonewtons per square meter. Okay, so this is the factoring moment that we calculated to get the bending for the main reinforcement, and this gives us the L, the span that we are considering is the shorter span, the minor, because the supports are here, and we are calculating on this. There was before another one-way slab. The supports were in different positions. That's why it was calculated for the major span in the previous. In this one is in the shorter span. That is what gives us less rebars, less steel to span. shortest span is always the best. Okay, 67. For the shear, factor shear, it's WF multiplied by the minor span divided by 2. That gives us 45 kilonewtons. So we can calculate and compare with the mil, that is the K that are in tables on British codes and many other codes. We calculate this, I call it mil, you can call it K. So here it's equal to the factoring moment divided by B, multiplied by the effective depth elevated by 2, multiplied by FCD that we have here, FCD of the concrete, 16.67 megapascal. So this will give us 0.056. It's a non-dimensional moment parameter. So we compare in the table for this concrete and this kind of steel. So the mil limit, this is what we calculated. The mil limit, we have this on tables, Eurocode. So if we go here check, we are using A400, it will be 0.391. That's where it's coming from. It's already calculated the limit of this non-dimensional parameter. So it has to be, what we calculate has to be minor than this, or equal. And it's checked, so it's simply reinforced. SLAB. The K1 and K2 are already fixed parameters for this kind of concrete. So strength of this concrete. With this we can get the percentage of the reinforcement that will have the main reinforcement. So it will be by this equation. And we have this one. You just need to put it there. We can see the equation, and we get the value 0.057% for reinforcement. We go to the equation of the main reinforcement, and we have the W multiplied by B. By this B, it's 1 meter that we are considering for a section of 1 meter. By D, that is in our case 0.27 meters. By FCD, that we saw already 16.67, and we divide by FYD. This is already FYD calculated here, 347. That we get from 400 divided by 1.15. Okay. All this, of course, we are using units in square centimeters per meter. So this is why we put here the equation this to convert everything. We get the square centimeter. Give us 7.41. 7.41. Well, and we need to make a check for the minimum reinforcement. And that minimum reinforcement is given by this equation. 0.26 multiplied by FCTM multiplied by the B section in the tension, multiplied by D divided by fyk. Fyk is characteristic value of A 100 of steel, so it's 400 megapascal here. So the FCTM it's on tables. You get this on Eurocode, and this is FCTM for this kind of concrete. We go here, table, FCTM C2530, FCTM give you 2.6. Putting all this and converting, of course, these values to centimeter, because we wanted square centimeter per meter. It gives us 4.56. Comparing this minimum value with the main reinforcement, we get the main reinforcement is okay, because it's bigger than the minimum. And for spacing, I always like to limit it to 25 centimeters for this kind of slab, the maximum limit. And for spacing, it's you can have this equation will be the minimum value between these two values, the 25 cm and 1.5 of the total depth. Which of them is smaller is this one that I use, and here is giving 25, so I use the spacing of 25. And to get this steel, I can't use it the 12 because it's giving 4.52, that is less than the minimum reinforcement required. So using bars with a diameter of 16 millimeters, I get 8.04 square centimeters per meter. So it's okay. Now that we have the main reinforcement here on the bottom, main reinforcement, we need to get the distribution bars on the bottom of the distribution bars, and the distribution bars are 20% of the main reinforcement. 0.20 multiplied by the main reinforcement that we calculated, and this is multiplied by this 0.20 multiplied by 7.41, that gives us 1.48 square centimeters per meter. And this is very small quantity. I like to use always the minimum reinforcement. I like to adopt, but we didn't need it. We are only obligated to calculate the main reinforcement and this on one-way slab, simply reinforce it. But I like to put always the minimum, and the minimum here is 4.56. It gives us 1.48. So if I place spacing 25, it gives us less than with a phi of diameter of 12, is less than the minimum of 4.56. So this is why I'm using spacing of 20, giving 5.65 square centimeters per meter. So and I don't use the 10 because it gives me 3.93, that's why. But I was needing only this. I'm going to 12, give me 5.65, diameter of 12, spaced by 20. So now for the sides where it can have some negative tensions on the supports on each side, and we need to calculate there some reinforcement of like cracks. And in the support will be the minimum value or 25% of the main reinforcement. And the maximum value of them will be what we're gonna get. So the maximum we get 4.56 square centimeters. So it's actually the minimum value that we calculate, so it's the bigger one. And so we maintain the same for the rebars reinforcement on the support. Diameter of 12 spaced by 20 give us this. Another distribution for the bars for distributions on the support. They have to be 20% of the what we calculated for the support, and what gives us a very small quantity. It's 0.2 multiplied by 4.56. It gives very small, and this, as you can see, we could even put like rebars of 6. You know, if we maintain the spacing by 20 centimeters, it still gives us a lot. But I don't like to use the 6 for these kind of things, and I will use the 12 spaced by 20, and this will give me that rule that I like to use, that is maintaining the minimum steel calculated. So we will get this. In the bottom of the slab, on the 6 meters, along 6 meters, we have the main reinforcement that will be diameter of 16 spaced by 25. This is the quantity, the area of steel. And then for the main distribution bars will be diameter of 12 spaced by 20. On both sides of the support, on the length, it is L, in this case the shorter one, 6 meters divided by 4, that gives 1.5 meters. It will be from there to the passing to the center of the support and passing more, then making a turn. Okay, so for the support, the reinforcement will be diameter of 12 spaced by 20, and as we calculate 20% of this, and it equals there in the minimum reinforcement phi of 12 spaced by 20. So we got a good reinforcement for this slab, and we have checked the flexion for the ultimate limit state, and we need to check the shear. So to know if we need the stirrups, and we have this equation from the Eurocode. Check shear at the ultimate limit state. We have the Vsd, it's the factor shear that we calculated for here on the top, 45 kilonewtons. So it has to be smaller than the shear resistance, that is this equation. And this one has to be bigger than this other one. Okay. In reality, what we are saying is that the factor shear reinforcement has to be smaller than the maximum of these two equations. here, smaller or equal, or the maximum of these two equations. So we have this one that we calculated the factor shear, and the shear resistance from here, that is the CRD. CRD is 0.18 divided by a safety factor of 1.5 gives us 0.12. Multiplied by K. This K is gotten from this equation, the D on millimeters, and gives us 1.86, and has to be less or equal to 2, and it's okay. If it was not, we will adopt the value 2. It's okay. So we're going to use 1.86. For in the equation we have K1 here, K1. So, but we don't have this value is fixed. We don't need to continue because we don't have an actual force on this example. So there is no tensile here, tension. We don't have actual force or per stressing. The row, for example, the row here, the row, it's calculated from this equation, the main reinforcement divided by B multiplied by D. What gives us, and it has to be smaller or equal to 0.02. So give us, when we make this calculation, give us 0.0029. What checks the equation? 0.02. So it's okay. When we calculate this, so we have the ultimate limit state of shear 45 is smaller or equal to this. It was the major value, maximum value of these two equations, and it was 117 that we have calculated here. So it was bigger than this one. What this means is that it's checked the safety for shear at the ultimate limit state, and you can see this on Eurocode 6.2.2. This equation is used for members not requiring shear reinforcement. So that's it.